Hi, welcome to the Mathemagic channel. Today we look at how to solve x to the power 4 equal -4. This is going to take us a little bit into the complex numbers. If you're ready, let's go. Alright, so I've seen this problem floating online recently and I've seen a lot of solutions of the form, okay, well, we're going to say that x is a complex number a plus bi, and if we put it to the power 4, we should get -4, and then we expand this, maybe we do some binomial factorizations and so on. This seems horribly complicated and super long, you guys, so probably this is not the quickest way you could go with a problem like this. So let's look for complex number solutions, and so in the real numbers, no solutions. So in R, there's no solutions. So we're going to look in C. And what I would encourage you to do here is to say something along the lines of x is equal to -4 to the power 1/4. Now, it's a little bit difficult to work with a -4 to the power 1/4, but what we can do is we can change -4 into 4e to the I pi to the power 1/4. The reason we can do that is because e to the I pi is simply equal to -1 using Euler's identity. And we probably want to simplify this problem as quickly as possible. And so instead of re-expanding this and just finding the one solution, why not just find them all right now? So we can add circles to this value, 4e to the I pi, when we simply multiply this by 1, and 1 in complex number form here in polar coordinates is going to be e to the 2 pi ki, so in exponential polar coordinates here, to the power 1/4. This is true because every 2 pi is going to be a full rotation around the unit circle, or in this case in the Argand diagram. And what we can do is we can just say that this is true because e to the 2 pi ki is equal to 1. Every rotation of 2 pi around the circle is just going to bring you back to your starting point. This is true as long as k is an integer, so as long as we say that k is equal to an integer z here, we should be okay. So something to bear in mind. And so now we can just distribute the 1/4 to everybody. So we can say we have 4 to the power 1/4. And then that's multiplied by e to the I pi to the power 1/4, so e to the I pi divided by 4. And we're also going to go around in circles by multiplying by 2 pi divided by 4, and 2 pi divided by 4 is going to be pi over 2. So we're going to make quarter circle turns. There'll probably be 4 solutions here. So it's going to be pi over 2 times the ki's. So I'm just going to put the ki's in bracket here. So starting with the constant term, 4 to the power 1/4, if we square root 4, we get 2. And if we square root it again, we'll get the square root of 2. So this is going to be the distance of all these points from the origin. We're probably going to have 4 points since it's an equation to the 4th power. And using power laws, we can say that this is e to the power I pi. And adding the powers, we'll have a 1/4 plus rotations of pi over 2i, so we can say rotations of 1/2 of k. So what that means in simple terms is that the first value will be pi over 4, and then we're going to rotate in 90 degrees, which will be pi over 2's, so rotations of k pi over 2's. Now, it isn't really important whether you express this in polar form or in cis form. Cis means cosine plus I sine, or if you write it explicitly as the square root of 2 times first the cosine of pi over 4 plus k times pi over 2 plus I sine. This is just an explicit form to help you locate the points if you're having trouble visualizing it. Pi over 4 plus k times pi over 2. Now the way that this is going to look, we know that pi over 4 is going to be root 2 over 2. So we know in general terms from trigonometry that the cosine of pi over 4 is equal to the sine of pi over 4, and they're both equal to root 2 over 2. So when you're taking 90-degree turns, and I'll make sure to illustrate that with a diagram for you right now, but first I'll write the solution set out in algebraic terms. It's going to be root 2 times plus or minus root 2 over 2 and plus or minus I times root 2 over 2. So we're going to have 4 different solutions here based on the rotations of 90 degrees. And if you simplify this, you're essentially getting plus or minus 1, plus or minus I, and those are your 4 solutions. We could simply write this in a solution set as x1, x2, x3, x4. And those values would be, so if we start with the first one, I would imagine that we have 1 plus I, and then as we keep rotating by 90 degrees, we still have positive I, we'll get negative 1 plus I, sorry, I'm just visualizing them, and then we'll get negative 1 minus I, and for your last solution, you'll have, let's see here, 1 minus I, that should be the right last one. And so these are your solutions for this equation, and you can verify this by putting these numbers, 1 plus I, for example, to the power 4, and checking that it's indeed equal to negative 4. Now you could represent this in exponential form and then put it to the power 4. It's pretty easy to check. Now for the visual representation, you can just imagine that we have a circle with a radius, which would be the square root of 2. And that we have 4 points which are perfectly rotated at 45 degrees from the origin and 90 degrees away from each other, or pi over 4 from the origin and pi over 2 away from each other. So this will be the first solution, so I'm going to call it x1. This will be your second solution, x2. Your third solution will be somewhere around here, and you can call it x3. And your fourth solution would be here, and it's called x4. Now, as you represent those, this will be your 1 plus I here. And then on the other side, you'll have negative 1 plus I. And at the bottom, you'll have negative 1 minus I. And then the last one here, which is 1 minus I. Remembering that this horizontal axis is the real axis and the vertical axis is the imaginary axis. And so what we can do is we can keep spinning around the circle, and we'll have an infinite number of solutions like that as long as we keep adding circles to these. You can also represent these with an angle and a length, what we call a modulus and an argument, to see that we have an angle here of pi over 4, which is 45 degrees, and the length, which is root 2, since we're around a circle that has length root 2. And so just to develop a good understanding of complex numbers here, you could also represent all of these values as root 2, so what we call the modulus, or the distance from the origin, times here e to the I pi over 4. And for this one here, you could also represent this as root 2 times e to the I 3 pi over 4. And this would be exactly the same value as this. And here you could have root 2 e to the I 5 pi over 4. That would be the same as that one. And then here, your last solution would be root 2 e to the I 7 pi over 4. So whether you choose to express your solutions as 1 plus I, negative 1 plus I, or any kind of Cartesian form, that's totally fine. If you choose to express them in polar coordinates, that's totally fine. If you like to use cis, that's totally fine. If you want cosine plus I sine, that's also totally fine. The main point is that you understand that we're going in rotations of pi over 4 from the origin, and that we're adding 90 degrees each time. And your 90-degree rotations are going to go like this. So it's a rotation of 90 degrees, or pi over 2. So we're adding pi over 2 every time. To go from one solution to the other, we just keep adding pi over 2 every time, which is equivalent to 90 degrees. And so we can keep doing that infinitely many times. And that's how you solve this beautiful equation. Thank you for watching the solution on the Mathemagic channel. Please like and subscribe so we can bring you more awesome math videos. If you enjoyed this one in terms of complex numbers, something to bear in mind is that this is nothing more than an exercise very similar to finding the fourth roots of unity, except for the fact that we've just multiplied them by root 2, and so that when you put this to the power 4, you obtain the value negative 4. Thanks so much for watching. See you on the next one.